and we learned that it has nice properties, namely covariant derivatives transform as tensors, which is what we want with the principle of general covariance. But we have to be careful because covariant derivatives don't obey all the same rules that ordinary derivatives do. So let's summarize. Covariant derivative of the sum is the sum of the covariant derivative. The covariant derivative of a product obeys the Leibniz rule namely, if I have two objects which could be tensors, I won't put indices on them. Their covariant derivative is A times the covariant derivative of B plus the covariant derivative of A times B. So that rule stays the same. Commutes with contraction. And the reason for that is that the covariant derivative of the metric is 0. So whenever we have a covariant derivative, we can pull the metric through without cost. And so V mu semicolon lambda is the same thing as G mu nu V nu semicolon lambda. But that's the same thing as G mu nu V nu semicolon lambda. Just tripping over my shoelaces here. Yeah.
I think of this operation using the, in this case, the inverse metric as raising and lowering, and when I hear contraction, I think of the Kronecker delta. Do I have the term swapped, or is contraction more general than I'm thinking of? Or does this also work with the Kronecker delta and not only with the inverse metric?
Okay, I guess you're right. The contraction, one speaks sloppily about contraction. I mean raising and lowering indices, but it's equally true for the Kronecker delta. I mean, contraction can mean that's the meaning of contraction you have in mind, yes? But whenever an indices is summed over, we use the word contraction also. So perhaps that's a misnomer, but we use the word contraction whenever we sum over an index. Any other questions? However, and this is crucially important, covariant derivatives do not commute. So you take V rho semicolon mu semicolon nu is not the same thing as V rho semicolon nu semicolon mu. And we'll see exactly how they don't commute in just a moment. Now, before I go on to talk about curvature, let me make a few more remarks. First of all, a little exercise. Let's suppose J mu nu, J mu nu rho, and J mu nu rho sigma are densities of weight 1. Show that J mu comma mu, J mu nu comma mu, J mu nu rho comma mu, and J mu nu rho sigma comma mu are also densities of weight 1. By here I mean tensor densities, of course. Naively, you might think they're not tensors because I've used the ordinary derivative instead of the covariant one. But here's one of those circumstances where the two coincide. So I can put commas or semicolons and I get the same answer. So I just want you to verify that. So we can see, I hope, where the physics of this is going. We've got a rule. If we know the right physics in flat space, we now have a rule for writing down the right physics in curved space, because the semicolon converts tensors to tensors. And it reduces to comma in the flat space limit, which means, in this case, in the absence of gravitation, so the rule is, write down the special relativity equation whatever it may be. Could be, say, Maxwell's equations that we wrote down recently. Everywhere replace the Minkowski metric eta mu nu by g mu nu of x. And by the way, this is usually called the Riemannian metric after Riemann, 19th century mathematician. And replace ordinary derivatives, which are partial derivatives d mu, or sometimes comma, by semicolon. And by the way, we sometimes use a notation grad mu for a covariant derivative as well as a semicolon. They're interchangeable. So here's your rule for getting the right physics in a gravitational field. You write down what you think is the right physics in flat space in the absence of gravity. Everywhere you see a Minkowski metric, you replace it by the Riemannian metric. And everywhere you see an ordinary derivative, you replace it by a covariant derivative. That guarantees that the equation you get will be generally covariant. Now, that's not entirely unique, as we'll see, but this prescription is known as minimal substitution. That's the very least you need to do to get the right equation. You could modify it by things that vanish in flat space. That would still satisfy the requirement that you reduce to the familiar equation in the absence of gravity. So that's why it's not quite unique. But this prescription is, on the whole, a reliable one, and that's all you need to do. Let's apply that rule to a case we're familiar with, Maxwell's equations. In flat space, we have f mu nu comma nu equals 0. And I'm just going to look at the source-free Maxwell equations for simplicity, where f mu nu is the curl of the vector potential A nu and the other one can be written f rho sigma comma mu plus f sigma mu comma rho plus f mu rho comma sigma equals 0. Now, there's an energy momentum tensor associated with the Maxwell field, which I'll just quote. F mu alpha plus 1/4 eta mu nu f alpha beta. And it has the property that it's conserved d mu t mu nu equals 0 as a consequence of the field equations.
What is the significance of the tensor? What is the significance of the tensor?
Of the energy momentum tensor.
Okay.
The energy momentum tensor will play a crucial role when we come to look at Einstein's equations. But for the moment, let's just regard it as a measure of the energy and momentum of the electromagnetic field in flat space. So now let's go to curved space. This gets replaced by F mu nu semicolon nu equals 0. F mu nu stays the same, by the way, because you remember when we take the curl of a vector potential, that's one of the cases where the ordinary derivative gives the same answer as the covariant derivative. And the same is true here. Because this combination, if I replace covariant derivatives by ordinary derivatives by covariant ones, I get back to where I started. You could write this as star F mu nu semicolon nu, where star F mu nu is defined to be 1/2 epsilon mu nu rho sigma F rho sigma. Now what happens to T mu nu? Well, it's the same on the understanding that the indices are now raised with G and not with eta. But this becomes a G. But something interesting happens. What was the ordinary derivative of t equals 0 gets replaced by the covariant derivative of t equals 0. And there's a physical significance to that, because this was telling us that in the electromagnetic field in flat space-time conserves energy and momentum. And now we see the ordinary derivative is no longer equal to 0. And what that means physically is that the electromagnetic field is sharing energy and momentum with the gravitational field. So separately, it isn't conserved. That's physically what you would expect, and the mathematics, in the clever way that general relativity does, takes account of that fact. So now we're going to move on to a new topic, which comes back to the fact that covariant derivatives don't commute, and it will be the topic of curvature. Any questions thus far? Yes? Roughly, good question, and I mean roughly speaking, yes. However, you're touching on a tricky point, because the whole definition of energy in curved space-time is a tricky one. And it turns out that you can only define what we normally think of as energy and momentum asymptotically, a long way away from the gravitational source. But that will, roughly speaking, what you said is right. But I just warn you that when you come to look at general relativity questions of energy and momentum are rather subtle. Now, I want to make sure I've got my indices right, so I'm going to check. Of course, Weinberg isn't infallible, but well, this is the equation I want to look at, so I'll leave it there. Let's look at V mu semicolon nu semicolon kappa. It's d by dx kappa of V mu semicolon nu minus gamma lambda nu kappa V mu semicolon lambda minus gamma lambda nu kappa V lambda semicolon nu. So I've just applied for the kappa index the rule for covariant derivative. But now I apply it on the new index, and I get d2v dx nu dx kappa minus dv d lambda dx kappa gamma lambda mu nu minus v lambda d by dx kappa gamma lambda mu nu minus gamma lambda nu kappa dv. This looks like a mess, but it's going to simplify in a minute. Plus gamma lambda mu nu gamma sigma mu lambda v sigma minus gamma. Can you all read the board here? Lambda mu kappa dv lambda dx nu plus gamma lambda mu kappa gamma sigma lambda nu v sigma. But now here's the nice part. V mu nu semicolon kappa minus the same thing with nu and kappa interchanged can be written rather neatly as minus V sigma R sigma mu nu kappa. And what is R sigma mu nu kappa? This is called the Riemann tensor. And you can see it's a tensor because the left-hand side of the equation is a tensor and V sigma is a tensor. So that means whatever this is has to be a tensor. And it's built out of gammas and their first derivatives. R lambda mu kappa equals d lambda mu dx kappa minus d lambda mu kappa dx mu plus gamma eta mu gamma lambda kappa eta minus gamma eta mu kappa gamma lambda mu eta. Now gamma, you remember, was not a tensor. The clever thing is that this combination of its first derivatives and products is a tensor. And it's the tensor that you get when you try and commute two covariant derivatives. You find that they don't vanish. And the amount by which they don't vanish depends on the Riemann tensor. Sorry, yes, that should be a new. Thank you. It's very easy to slip an index in this game. You have to be careful, but it's crucial that you get them in the right place in the right order. So the necessary and sufficient condition that that derivatives commute is the vanishing of the Riemann tensor. We can generalize this to higher rank tensors. For example, if we have a two-index tensor, rho, semicolon, sigma minus t mu nu, sigma, semicolon, rho, then there's one term for one index, mu, rho, nu, t, lambda, and then there's one term for the other index.
If the Riemann tensor vanishes, what is that type of measure? What can we deduce?
I'm just about to. That's the next topic in my discussion. Is precisely that. So ask me again if you don't understand what I'm going to do. So this brings me to my next point, which is conditions for flatness. In flat space, the line element can be written ds squared is eta alpha beta d psi alpha d psi beta, where eta was minus 1, 1, 1, 1. In curved space, we have g mu nu of x, dx mu, dx nu. However, the x dependence here is rather a poor guide as to whether the space is really curved or not. Because I could get an x-dependent g mu nu by going to a different coordinate system, even in flat space. For example, so x-dependence does not guarantee curved space. Let's look at it an example. Suppose we have not Cartesian coordinates, but polar coordinates, t, r, theta, phi. Then in those coordinates, g mu nu depends on x. It looks like minus 1, 1, r squared, sine squared theta. So that ds squared is minus dt squared plus dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. So even a flat space metric, when written in polar coordinates, depends on the coordinates. So you can't just look at the x dependence in the metric and say, aha, that means the space is curved. Just as a matter of interest, the coordinate transformation you need to go from one to the other is sine naught is t, this is r sine theta cos phi, r sine theta sine phi, and r cos theta. So just transforming from Cartesian coordinates to polar coordinates gives you a metric that depends on the coordinates, but it doesn't mean that space is curved. It's just flat space written in polar coordinates. And the answer, and this answers the question that was just posed, how do we tell whether the space is curved or not? The necessary and sufficient condition that G mu nu be equivalent to the flat space to the Minkowski metric. Is that the Riemann tensor vanish everywhere. So the way we can tell that this is not a curved space and just a flat space in disguise is to compute its Riemann tensor. And we'd find it's 0, just as the Riemann tensor of the Minkowski metric is 0.
Does that condition have implications for gamma?
Yes. It means that gamma needn't be 0, but its first covariant derivative and product combination that forms the Riemann tensor must be 0. In fact, I'm going to give you an example of that now. So we can adopt this as a definition, really. Lambda mu nu kappa equals 0. We say space-time is flat. And if it's not equal to 0, we say space-time is curved. So that's the criterion, not whether G mu nu depends on x or not. So let's go back to our fellow in the elevator. In this case, the Riemann tensor is 0. There's no gravitational field. Neither gamma nor Riemann is 0. So in this case, gamma was non-zero, but R is still 0. That's the homogeneous gravitational field case. But you can go to a frame where gamma vanishes. The genuinely curved space situation is here. And once again, the word tidal is used. Tidal effects mean non-zero Riemann tensor. So a uniform gravitational field is a sort of a confusing exception to the rule. There's a gravitational field, but space-time is still flat. To get a curved space-time, you need an inhomogeneous gravitational field. So it should be obvious, I think, that this Riemann tensor is going to play a very important part in our analysis. Yep.
But can you explain why in the first case gamma is 0 and what is the second case is not 0?
We That's the equation that the baseball follows generically. Now, you remember in going from here to here, we did a transformation. I'm trying to remember what it was. X prime is x minus a half gt squared, I think, which ensured that although gamma was non-zero here, when you go to this frame, it's 0. That in the freely falling frame, it's as though it was in special relativity. But when you, in order for there to be an acceleration, we need gamma to be non-zero. However, because it's homogeneous, the Riemann tensor vanishes. Here, gamma is not 0, and neither is Riemann. We can put gamma equals 0 at a point in the freely falling frame, but only locally. Globally, it's not 0. So this Riemann tensor is going to play a crucial role, and we're going to look now at some of its properties. Algebraic properties of the Riemann tensor. Those of you who are familiar with Maxwell theory, or perhaps Yang-Mills theory, will recognize the Riemann tensor as being like a field strength. In Maxwell theory and Yang-Mills theory, you have a potential, and the curl of the potential is the F mu nu, and it's the vanishing or not of the F mu nu that tells you whether you have something which is a genuine force rather than one that can be gauged away. And here it's playing a similar role in gravity, that the gammas are like the potentials and the Riemann tensor is like the F mu nu, the field strength. And the fact that we can't gauge away the gammas, which we can in the case of a homogeneous gravitational field, tells us that the Riemann tensor is non-zero, or vice versa. Now we can lower the index. It started out life with 1 index up and 3 indices down, if you remember. That's how we defined it. We can define one with 4 indices down like that. So that's not the right index. There we go. And for what it's worth, you can write this in terms of second derivatives of g. Plus the product terms. And from that, or otherwise, you can deduce some symmetry properties that the Riemann tensor needs to have. So Riemann 4 indices, if we interchange the indices like this, we get back to where we started. So we've taken the first two and we've swapped them for the second two. There's also some anti-symmetry. If we interchange the first two, we get a minus sign. If we interchange the last two, we get a minus sign. And if we do both, we get back to where we started. Then we have what's called cyclicity. If we take three Riemann tensors, lambda, mu, nu, kappa, plus lambda, kappa, mu, nu, plus lambda, nu, kappa, mu. So we've done a cyclic permutation on the last three. If you add them up together, you get 0. So you may ask, how many independent components does the Riemann tensor have? And I leave this as an exercise. The answer is 20. Yep.
Would you mind clarifying what you mean by independent components?
Yes, if you give me, if I want to reconstruct the tensor R mu nu lambda mu, how many numbers do I need? And the answer is 20 numbers is enough to give me the whole tensor. Because if I know R01 mu nu kappa, I know R10 nu kappa. So that's, the other one's redundant. I already know what it is. Yeah. Sorry, was there a comment? Sorry, my hearing's not very good.
Is it only valid for some coordinate basis?
No. No, it's a coordinate independent statement. The number 20 is all we need. And notice, by the way, that if we trace over lambda and mu we get 0 because of that antisymmetry property. But we can define something called the Ricci tensor, R mu kappa, where we trace over the first and the third. And this is a symmetric tensor. And the Ricci tensor will play an important part in what we're going to do. Let me, before we do that, define two other important tensors. There's the curvature scalar, which is just the contraction of the Ricci tensor, G mu nu R mu nu. And then there's the Weyl tensor, which is normally written with a C, rho, sigma, mu, nu. And this is the Riemann tensor with some subtractions. Now, what's so special about that? The Weyl tensor has the important property of tracelessness. G, rho, mu, C, rho, sigma, mu, nu is equal to 0. Now, those are algebraic properties. We haven't differentiated anything yet. That's just the Riemann tensor itself. There are also some identities that the derivative of the Riemann tensor satisfies, which are known as Bianchi identities. Let me resort to the other notation here. It's more convenient. the covariant derivative of a Riemann tensor is identically equal to 0. I could abbreviate that by lambda mu nu kappa semicolon eta anti-symmetrized on the 3 indices. Now, you can verify that by slogging it out, writing out the Riemann tensors with all the gammas and filling the blackboard that way. You would convince yourself it was true. But there's a quicker way of doing it, which I leave it to you. Use the Jacobi identity. Applied to covariant derivatives. Do you all know what the Jacobi identity is? It says if you take a commutator of grad mu with grad nu, and then take the commutator of that with grad rho, and then you do the add it cyclic permutations, so this would be grad rho, grad mu, comma, grad nu. Brackets mean commutators, plus brackets, commutator, grad nu, grad rho, grad mu. And that's identically equal to 0, just from the properties of a commutator.
I think that last covariant derivative should be respecting u. Last covariant derivative, first line.
Yes, eta, kappa, nu. Thank you. Yes, thank you very much. So I leave you to verify that this is true. We can contract with G lambda nu, and we get R mu kappa semicolon eta minus R mu eta semicolon kappa plus R nu mu kappa eta semicolon nu equals 0. And again, R semicolon eta minus R mu eta semicolon mu minus R nu eta semicolon nu. And this is interesting because it implies that the covariant derivative of something I'll call G mu nu is identically equal to 0, where G mu nu is called the Einstein tensor, and it's defined to be the Ricci tensor minus 1/2 G mu nu R. You often see these cartoons where Einstein writes E equals mc cubed and crosses it out and then writes E equals mc squared. An equivalent cartoon is how he defined the Einstein tensor. First of all, he had an r mu nu minus a quarter g mu nu r. And only later did he realize it was actually a half. He wanted the quarter because that was traceless, but that was not a good reason. The fact that it obeys this equation is crucial because we've just seen another tensor that obeys that equation, namely the energy momentum tensor. And we'll see in subsequent lectures that the Einstein equations are simply to equate the Einstein tensor with the energy momentum tensor. But there's a subtle combination of physics going on. The reason why the energy momentum tensor obeys the condition is to do with conservation of energy. The reason the Einstein tensor obeys this condition is because of some differential geometry. But the two are all nicely entangled in the general theory of relativity. Well, we have one more topic to cover before we get on to Einstein's equations, which has to do with geodesics. But I'll leave that for Monday. Are there any questions? If not, have a good weekend. Bye-bye.